Okay, we look at continuity of a function of more than one variable. When do we say a function is continuous? Now, mostly continuity is defined at a point. So we want to check whether a function f of p is continuous at the point A. Okay, let me just say, let's say f of maybe x, y is continuous at the point a1 and a2. All right. Now, a function f of p is continuous at the point a. One, if f of a exists. Number two, if the limit as p approaches a, f of p also exists. And three, if 1 is equal to 2, that is if f of a is equal to the limit as p approaches a, f of p. If all those three things here are satisfied, then we say that the function is continuous at the point A. The function is continuous at the point A. If any of these, if it doesn't conform to this, then we say the function is discontinuous at the point A. Let's look at an example. Determine whether J is continuous at a point 0, 0. If so, we want to find whether the point J is continuous at 0, 0. Okay, and we say G of x, y is equal to x4 plus 2x squared plus 2y squared plus y4 all over x squared plus y squared, and here it is 2. Now here is if x, y is not equal to 0, 0. And here we say if x, y is equal to 0, 0. Now, it's an example, Now, we use the definition. So here, if the function is continuous at the point 0, 0, then 1, g of 0, 0 must exist. Now, what is g of 0, 0? Here, if xy is 0, 0, then the function is equal to 2. If xy is not 0, 0, then the function is equal to what we have here. So clearly, g of 0, 0 is equal to 2. I hope you got that. Good. Number 2, we find limits as x, y approaches 0, 0 of the function x4 plus 2x squared plus 2y squared plus y4 all over x squared plus y squared. We find this limit. What it means is that we take it through the accumulation point theorem. We find limits along all the lines which pass through the point 0, 0. And if you are getting the same limits along these lines, then we use epsilon delta definition to verify whether the limit exists and it is that which we claim to be. And clearly, we solved this question before in our previous lesson. And this we had was equal to 2. So clearly, since 2 here is equal to 2, now since here 1 is equal to 3, is equal to 2, sorry, we claim the limit exists. Sorry, we claim the function is continuous at the point 0, 0. Let me take it again. Since g of 0, 0 is equal to 2, and the limit as xy also approaches 0, 0, of the function is also equal to 2, and the two are equal, 1 is equal to 2, we claim the function is continuous at the point 1, at the point 0, 0. Okay, another example. Another example. We want to determine whether the function h is continuous at 0, 0. Where here h of x, y is defined as x, y all over x squared plus y squared. Now here, okay, it's 2, Now here, if x, y is not equal to 0, 0, and here, if x, y is equal to 0, 0. Alright, so we check. 1, we look by definition, we check h of 0, 0, and here is equal to 2. 2, we find limits as x, y approaches 0, 0 of x, y over x squared plus y squared. So we use calculation for the square, right? Okay, so we find limits along x, we find limits along x is equal to 0. Now if x is 0, right, then I'll have limits as y goes to 0, limit as y goes to 0, 0 over y squared, which is equal to 0. And I find limits along y is equal to 0. If y is 0, then limit as x goes to 0, y is 0, it will be 0, I have 0 over x squared, which is also equal to 0. Next, I find limits along y is equal to x. In place of y, I put x now, and I'm going to have limits as x goes to 0, x squared over x squared plus x squared. The one I put x here, I get x squared here, okay? And clearly this is equal to half. Now you see, along the line x is equal to 0, I had 0. Along y is equal to 0, I had 0. But along y is equal to x, I'm getting half. So here I conclude that the limit does not exist. Once the limit does not exist, it means that the function is discontinuous. Remember we said that all the three conditions must be satisfied. Once 2 does not exist, we claim that the function is discontinuous at a point 0, 0. Okay. Now we have two types of discontinuity. We have two types of discontinuity. A discontinuity that is essential and a discontinuity that is removable. Now let's see. When do we say a function is continuous at a point? 1. If a function is continuous, f of p is continuous at a point A, right? Then 1. F of A must exist. 2. Limit as P approaches A, f of P must also exist. And 3, the 2 must be equal. That's 1 must be equal to 2. Now, if this exists and this exists and they are not equal, it is discontinuous. But we say that discontinuity is removable. We can remove discontinuity. Okay? Remember, let me take it again. If this exists, and the 2 are not equal, we say that it is discontinuous. We say that it is continuous, but we can remove the discontinuity. So we say that the discontinuity is removable. Now, if this does not exist, the discontinuity is essential. If this does not also exist, the discontinuity is essential. Okay, so if either of these does not exist, we have an essential discontinuity. But if they both exist but are not equal, we say that the discontinuity is removable. All right. Now,